Rank of A is the dimension of the column space of A. Rank. If two matrices are row equivalent, then their row spaces are the same. True or false? True. And the row space of A is equal to the column space of, yep, A transpose. Good. All right, so today we're going to define the row space. The row space is the set of all linear combinations of the rows of a matrix. So it's just like the column space, except now you're looking at the rows instead of the columns. And the rank of a matrix, which is just the dimension of the column space. Remember, the dimension of a space is the number of vectors in its basis. So this is just another little diagram to help us keep some of the terminology straight. We have two spaces. The domain, if you're thinking about a transformation, T of x equals AX, here's the domain. And within the domain, we have the row space and the null space. And then here's the range. Within the range, we have the column space, the row space of A transpose, and the null space of A transpose. So it's probably worth noting that the row space of A transpose is the column space of A, and vice versa, right? The row space, the column space of A transpose is the row space of A. Because the definition of a transpose is you take all the rows and make them columns, so those things flip-flop. All right, so I have three row equivalent matrices here, A, B, and C. So it's just to save us time. We don't have to do any row reducing. They're already written out. I want to find an example vector in the column space, the row space, and the null space of A. All right, so let's look at the column space of A. So I just want one vector. I'm not looking for a basis or like every vector. Yeah, so this is a pivot, right? So then you take that column from A. So that column would be in the basis, which means that it's also in the column space because the basis, the column space is a linear combination of all the vectors in the basis. So I can put 1, 0, 3, -3 there. There's a vector in my column space. My row space. All right, so the way you find the row space of a matrix is that the non-zero rows of any echelon form of your matrix form a basis for the echelon form and for the original matrix. So we pick any non-zero row from an echelon form, so any non-zero row from B or C, those are both echelon forms. So C is just the fully row reduced version where you have ones in your pivot positions. So any non-zero row from B or C would be in the row space of A. Row 2, okay. From B and C are the same. So I tend to write vectors from the row space horizontally to remind myself that they were rows and not columns, but you can write it either way. So I'm going to put 0, 0, 1, 0, 0, 0, 1. You could write that as a vertical vector too. All right, and then an element from the null space of A. So remember, the null space is the set of all things that get sent to 0, 0. So if I wanted to find a basis, how do we do that? You row reduce with a 0 augmented, and then the solution set, put it in parametric vector form. The vectors form your basis. So I could do that. I have the matrix already row reduced. I could just throw some zeros on the end and put it in parametric vector form. But I'm going to cheat a little bit because what vector always goes to 0? What vector is always in the null space? The 0 vector. In fact, the 0 vector is in every vector space, so I could have listed the 0 vector as all three of those things. So if I want to put the 0 vector as in the null space, How many entries are in that 0 vector? 7, yeah. Because remember, things that are in the null space are things that you would multiply by to get the 0 vector as an output. And so it would have to have 7 entries, the number of columns of A. So 1, 2, 3, 4, 5, 6, 7 zeros. And I'm going to go back and find a basis for null A in the next example. So we'll just use the 0 vector for now because it's easy. All right, the rank of A, that is the dimension of the column space of A. So how would I figure that out? The number of pivot columns. So I've got pivot, 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 and that's it, right? I have 3 pivot columns. So those 3 columns from the original A would form a basis for the column space, which means that I have 3 vectors in the basis, so the rank is 3. All right, the dimension of the null space. So if we think about how you find the dimension of the null space, first you have to find a basis, and you would write the solution set in parametric vector form. Each free variable gets a vector, right? You write it in parametric vector form where each free variable is sort of pulled out. So how many free variables do I have here? 4. So that's going to be the dimension of the null space, right? Because this is free, 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 free. The dimension of the column space of A, that is the same thing as the rank, so that's 3. The dimension of the row space of A. So the way you find a basis for the row space, remember, is the non-zero rows of any echelon form. How many non-zero rows of B do I have? 3. The last row is all zeros. So the dimension of my row A is 3. There will be 3 vectors in that basis. Okay, so the column space of A is a subspace of R what? 4. Yeah, it's because the column space is the set of all linear combinations of the columns. That's just the definition of column space. And if you take linear combinations of the columns of A, you're going to get vectors in R4. How about the null space? Subspace of R what? 7, yes. Because remember, the null space is things that get sent to 0. So things you would multiply by to get 0, and you can only multiply a 4 by 7 matrix by a 7 by 1 vector. It's terrible. R7, okay. The row space, if you take linear combinations of the rows of A, where do those vectors live? R7. There are 7 entries in each row. So you're taking linear combinations of the rows, right? They each have 7 entries. So they live in R7. Right, yeah. Yeah, if you go back to this picture, stuff in the row space has to have the same dimension as the null space, subset of the null space also. Oops. All right, the column space of A transpose. Well, the column space of A transpose is just the row space of A, right? And we already know that the row space of A is a subspace of R7. The null space of A transpose. Yes, awesome, R4. And you can also just picture transposing A, right? So then it would be 7 by 4. And if you are taking the null space, that's the set of things that get sent to 0. They'd have to have 4 entries. And the row space of A transpose, that's just the column space of A, which we know is a subspace of R4. All right, so now we're actually going to find a basis for the column space, the row space, and the null space of A. So I'm going to need these matrices that are row reduced here. Take a picture. All right, so column space. So a basis for the column space is just the pivot columns from the original matrix A. So you go to the RREF form and you identify the pivot columns as 1, 3, and 4. So you go take 1, 3, and 4 from A. So 1, 0, 3, negative 3. 0, 1, 0, 3. And negative 1, 0, negative 2, 2. All right, so that's my basis for col A. That one's easy. Basis for row A. Those are just non-zero rows of any echelon form. So I could take the non-zero rows of B or C, doesn't matter. So if I use B, I would have 1, 2, 0, negative 1, negative 4, negative 2, 0, 0, 0, 1, 0, 0, 0, 1, and 0, 0, 0, 1, 4, 2, 0. Or first 3 rows of C will also give you a basis for the row space of A. All right, now for the null of A, that is not quite as easily read directly from the matrices given, though they're going to help. You have to do a little bit of work, right? So the definition of the null space is the set of all things that get sent to the 0 vector. So you would take A, augment with zeros, and find the solution set. So what you're going to get is C augmented with zeros. So if I have A augmented with zeros, that's row equivalent to C augmented with zeros. The zeros just are never going to change. So if you just imagine zeros augmented on the C, then this says that x1, x3, and x4 are your basic variables. All the rest are free. So we have x1 plus 2x2 equals 0. That's what the first row would translate to. The next row says that x3 plus 1, 2, 3, 4, 5, 6, x7 equals 0. And my last row says that x4 plus 4x5 plus 2x6 equals 0. So then I would solve for my basics in terms of my frees, write it in parametric vector form. So I'm just going to jump to parametric vector form. So I have x, meaning x1 through x7, equals, and I get a vector for each of my frees, which are x2, x3 was a pivot, so that's not free. X4 is a pivot, that's not free, so x5, x6, and x7. So then I just have to figure out what goes in these vectors. I think I like writing this as x1 through x7. Okay, so x1 is negative 2x2. So I put a negative 2 in the x1 spot, and I put zeros everywhere else. Okay. x2 is a free variable, so the x2 vector gets a 1, everything else gets a 0. And x3 is a pivot or a basic variable, so it's negative x7. So x3, I put a -1 in the x7 vector and then zeros in the other three. x4 is a basic variable, and x4 is -4 x5 minus 2 x6. So I put a -4 in x5 and a -2 in x6, and the other ones get zeros. And then x5, x6, and x7 are all free. So x5 gets a 1, where the others get zeros. x6 gets a 1, the others get zeros. And x7 gets a 1, and the others get zeros. So that's my parametric vector form of the solution set to the set of all things that A sends to 0, AX equals 0. So those vectors that show up in parametric vector form, those are my basis for the null space. So I don't really want to write it again, but I'm going to, just to be really clear. Basis for null A is -2, 1, 1, 2, 3, 4, 5 zeros. 0, 0, 0, 4, 1, 0, 0. 0, 0, 0, -2, 0, 1, 0. And finally, 0, 0, -1, 0, 0, 0, 1. So there's my basis for null A. It's got 4 vectors in it, which we already knew it was going to have 4 because there were 4 free variables. Yes, thank you. All right, how many vectors are in the column space of A? There are 3 in the basis. How many are in the whole space? Infinite, yeah. There are infinite vectors in the column space of A. Because the column space is the set of all linear combinations of the vectors in the basis. And since there are infinite scalars, there are infinite vectors in the column space. So give me one vector in the column space of A that's not in the basis and isn't the answer we gave for part A, which also was in the basis. So just give me one vector in the column space that's not in the basis. 2, 0, 6, minus 6. Any multiple of these or any linear combination of these 3. You could add 2 together, could add all 3 together. So I like 2, 0, 6, -6. Any multiple of them. How about a vector in the row space that's not in the basis? Same thing. You could take any multiple of the ones I gave you. You could add add 2 of them together, take a multiple and add it to another. So let's see, what did I do? I think I added 2 together. I added the second 2 together, and I got 0, 0, 1, 1, 4, 2, 1. And a vector in the null space that is not in the basis. So this is my basis with 4 vectors in it. The null space is the set of all linear combinations of those 4, so you can add them all together. You could add 2 together, take a multiple of one and add it to a multiple of another. And let's see, I think I added 2 together again. I added the first 2 together. So I get -2, 1, 0, -4, 1, 0, 0. All right, so that finishes the demo for class 28, you can go ahead and start the activities.